Hello, we are the Naval Academy SUAS competitors. We'll be talking about our flight readiness presentation. So the first thing we want to talk about is our RMRC manufactured Anaconda airframe. And this is a picture of it right here. And here are some of the specs. So in the next slide, we'll show you some of the three places we have some things. So we have the payload bay rear at the bottom, right by the rear wheels. In the front, we have the payload bay front, the payload bay center.
So the first part of our hardware overview is the battery. We got 2 LiPo batteries, and we are using a parallel connection between them.
The next part we have is the receiver series. So we have the first receiver, which is going to be communicating with our safety pilot. And then we have a safety multiplexer. So the multiplexer is going to allow us to use manual and autopilot controls at the same time, so that if autopilot fails, we're not solely using manual through autopilot. We'll be able to take control if that system fails.
Next, we've got our autopilot, which is the Pixoc 2.1 Blue Cube, our telemetry radio, the battery monitoring to make sure we know what the batteries are at, and our pilot input is a RC-DSM remote receiver.
So we have an integrated sensor package for our unmanned sensing. So we have the RTK GPS, we have our compass, our gyro and accelerometer. So these are the systems that we're going to be using for our control systems. We have airspeed sensor as well on board.
Finally, we got some hardware we're going to use for future use. We have our high bandwidth radio, the TrendNet. We have a PoE injector and a single board computer. We are going to use all of these different hardware systems in future use, since we are not doing some parts of the competition this year.
So all these components are going to be fitting together into our interchangeable airframe that we have several of, and we'll do this using a custom-made cradle, and they all fit together in this space, and we will achieve those 2 mission areas of interoperability and autonomous flight with room for future development in the next competitions.
So here we have the cradle. All the components are mapped out in specific spots in the cradle, and it's very useful because we can just pick up the electronics from one airframe and plop it right into a new airframe. And the battery housings are also very useful here because they are movable, adjustable. And so we can shift the center of gravity of the airframe depending on the payload. The software system we're using goes through the Pixoc. That's our autonomous flight, and we're using the ArduPilot software through Mission Planner. And it's a very nice system because you can set waypoints very easily, and the waypoints can basically do whatever you want them to. You can have the aircraft fly to a waypoint, loiter around a waypoint, take off, land from waypoint, and you can also set the speed, the altitude, and other variables, which are very nice. And we're going to be using MATLAB for post-flight processing information.
For this year's competition, we will be attempting the autonomous flights and the waypoint performance. Sadly, we will not be competing in the obstacle avoidance performance, imaging, detection, classification, localization, mapping, and airdrop performance. All of the tests that we are not doing this year, we plan to do in future years. So we did a lot of developmental testing. We started off with the aerodynamics of the actual fuselage, and with the TrendNet on board, we tested the thrust because we added a bunch of weight with the internals. So we have to make sure that our propeller is good enough for flight. And then we started doing test flights. Our first flight was unsuccessful, but we learned a lot of data from it. Our second flight, once again, was unsuccessful, but we learned that our ESC was overheating. So that was the main thing we had to fix from that. And then we got it so we could do a full autonomous test flight with 5+ minutes of flight in the air.
Yep. So the very first test that we completed was the aerodynamics testing. So what we did is we had 3 different tests that we completed. One with the fuselage only, one with the TrendNet antenna added, and one with the battery canister added. So the main goal and mission behind this was to see how our external attachments on our fuselage would affect drag. So from our first experiment with just a fuselage, it had about 3.5 newtons of drag. After adding the tread net antenna, it added another 1.5 newtons of drag. And after adding the antenna and the battery together, it added approximately 2.8 newtons of drag, resulting in a total drag of all of our components together of 6.3 newtons.
And later, we carried some thrust testing to make sure that the thrust that was provided was enough to propel our aircraft with all the new drag. And this is a video showing the testing. So as seen here for our first flight test, we had some issues and crashed. The nose wheel was not wired correctly, which forced the pilot to over adjust the flight controls, and the rotation happened too early. And
Yep, and so you can see. So this time we and it was a very successful flight. It was 1 minute and 42 seconds of successful flight time. And at that 1 minute and 42 second mark, we encountered an issue with the ESC overheating. So as you can see, the green part is our power flight, which lasted for 1 minute and 42 seconds. And then at that X part, we had an ESC failure, which is where we glided down into our power up landing point, which is where we also encountered another issue. So as you can see, that's what the problem was. The ESC overheated mid-flight. And so during our powered off landing, we broke the front nose gear. So that was a second recurring issue that we've had with the nose gear being weak. So what we learned is that we needed to increase the amperage tolerance of the ESC in order to avoid it overheating during the flight. And it can also increase its flight time. We also need to beef up the nose wheel, especially around the styrofoam, in order to have just a stronger gear so it can complete land, or it can successfully land.
Here shows some testing that we did for the 60 amp ESC that we had, and then new 80 amp ESC. Testing was early with touch of hand to the results that we got were 4 minutes of flight time that can be done with a 60 amp ESC before it heated up and was not operational anymore. And one of the main reasons for overheating was also the ventilation, the heat sinks that were not so effective. For the 80 amp ESC, however, it took much longer time for it to heat, and we did not carry any flight testing for it. However, we're confident that it's capable of maintaining a good temperature all through. So this is the new ESC that we're using, the Cobra 150 amps, and the old ESC that we're using was the Hobbywing Flight 160A. Our performance for the autonomous flight was pretty good. For the most part, waypoints were targeted by around 20 feet. The only challenge that we could face here was with sharp turns. This footage shows about 5 minutes of autonomous flying before we landed manually.
Then lastly, we were asked to score ourselves on the criteria that was provided by us. And between our 2 autonomous test flights, the other many manual test flights, we've come up with these scores, and we feel confident in ourselves and our team that we're going to come out to this competition and do a good job. Thank you.